Hopefully, today's critical numbers. Unfortunately, you can't do critical numbers unless you know differentiability. So again, I have to teach a little out of order. Differentiability has to come first. So, there are some times when a derivative doesn't exist. Actually, 3 times when a derivative doesn't exist. You need to have those down cold, be able to deal with problems where derivatives don't exist and make it so the derivative exists, and then also prove the derivative doesn't exist. Lots of different stuff here going on. So let's try this. If I said use the alternate definition of the derivative to find the derivative of f of x equals the absolute value of x minus 2 at x equal 2 and sketch a graph, this will be a good review of the big idea of derivatives. So would you sketch the graph for me? What is the derivative, or sorry, what does the graph of absolute value of x minus 2 look like? A line shifted right 2, and instead of the negative part actually happening, the negative part gets flipped up, and so we're getting this kind of shape. Is absolute value always a v? No. Does absolute value always cause negative y's to be made positive? Yeah, it depends on what you're taking the absolute value of. In this case, you're taking the absolute value of the line. That's why it makes a v. But if I had different graphs, it wouldn't be a v. It could be a w. All right. So are we good so far? All right. Now recall, back in the day, when you first learned the definition of the derivative, there were a couple, and one was to say, start with the slope between 2 points. I'm going to call them x, some general x on any point in the curve, and 2. And say, what's the slope between these two? Now this point is x, f of x, and this is 2, f of 2. Do you agree? What's the slope between them then? Talk to me, people. F of x minus f of 2 for the rise. And the run. F at, or x minus 2, sorry, yes. Right? Now, wouldn't you agree that that gets you the slope between 2 points? And that's called what kind of slope? Secant slope. Now, the whole idea of a derivative then is to get the points closer and closer and closer and closer together. And so if I do that, then what approaches what? Is this h approaches something, or is this x approaches? Okay, I want to let x approach 2. You with me so far, people? Yeah. Okay, cool. Now, here's the problem of the day, though. It kind of depends on if the x is above 2 or below 2 as to what kind of slope you get. So write yourself a note. If x is right of 2, then you're talking the limit as x approaches 2 from the right of f of x minus f at 2 over x minus 2. What does that slope look like? Positive, what? Isn't the slope just the slope of the line on that side? What's the slope of the line? 1. Okay. Now, what if, however, there's no reason that x has to be over there? None. X could be over here. And I could say, now find the slope, and get a little closer, and now find the slope, and now find the slope. Well, if I take x's left of 2, then x approaches 2 from the left, comes out to be negative. What happens when you do a limit and the one-sided limits don't agree? One-sided limits not equal, then what? The limit doesn't exist. Well, in this case, the limit represents what's the derivative. And so if the limit doesn't exist, that implies f prime at 2 does not exist. I can't say, hey, what's the slope of 2 because I'm getting two totally different things. On this side, it looks like it's 1 on this side. But on that side, it looks like it's negative. Well, you can't say that's both. It's one or the other, and if it's not the same, then you say the limit doesn't exist, and therefore the derivative doesn't exist. So you're going to get a problem with the derivative anytime the slopes abruptly change from one thing to another without smoothly transitioning. At places where the derivative doesn't exist, then you would say we were able to take a derivative or differentiate. The vocabulary then is that at 2, the function is not differentiable, not able to take a derivative. There are 3 big reasons you need to commit to memory why a derivative doesn't exist. One is like we just had. Anytime you have a sharp turn like this, the one-sided slopes are not approaching the same value. You could say, write yourself a note, slopes must smoothly transition. Then, would you also write a little bit of vocabulary that other textbooks definitely use? Slopes must be locally linear. If you, for example, put a little microscope on this, the slope is going something like from -2 to +2, and there's no smooth transition, just boom, from one to the other. Well, that means that the limit doesn't exist, the slopes are not gradually transitioning. Now, if you had a parabola, it wouldn't matter that this side was -2 and this side was +2, because it smoothly transitioned from one to the other. If you were to zoom in here, it would look locally linear. The derivative exists. So if you get a place where there's an abrupt change of slope, not locally linear, then the derivative won't exist. At a discontinuity, say like this. Now I can't do the definition of the derivative here. For example, here. How could you do the alternate definition of the derivative there if f of 2 doesn't exist? If a point doesn't exist, you can't find the derivative there. That goes obviously for asymptotes as well. You can't find a slope at a point that doesn't even exist. That stands to reason. All right, last but not least, we get this all the time. When you get a derivative with 0 in the denominator, that's a vertical tangent. Here, the derivative is undefined, and so does not exist is the third case there. So there are 3 cases where the derivative won't exist, or a function is not differentiable. Where there's a sharp turn, where there's a discontinuity, or if there's a vertical tangent, it's undefined slope. Now let's look at a few problems, and then we'll get to the second part of the lesson. So first, on a case like this, if I said, determine is this function continuous and differentiable at x equal to, showing appropriate justification. So first of all, continuous. That's a review. How do you prove something's continuous? What's the first condition? Does the point exist? Does f of 1 exist? Is it defined? Yes, f of 1 is, wouldn't you agree that we're talking this rule, so it's 4 times 1, so it exists. Yeah? All right, what about the left-hand, right-hand limits? The limit as x approaches 1 from the left, which function do I use? 2x squared plus 2, and there is, what does that approach as x goes to 1? 4. What about the limit as x approaches 1 from above? 4. So can we conclude that the two-sided limit exists? The limit as x goes to 1 exists. Because the two one-sided limits are the same, yeah? And therefore we conclude that because f at 1 equals the limit as x approaches 1, that f is continuous. Do we agree? Now write yourself a note please, if you find not continuous, then don't even try differentiability. Because the minute you see something's not continuous, well, differentiability's out the door. If it is continuous, then there is a chance that the derivative exists there. Question is it smooth? All right, now what you're talking about here is a parabola and a line. And that could be a smooth transition of slope if you're talking just the right situation. If for example, the line meets the parabola there, well, surely that's a sharp turn, that ain't happening. And if it meets here, then that's a sharp turn, that's not happening. The question is, maybe there's a place over here where the green slope is just like where the red slope is handing off, and maybe it smoothly transitions. That's really the question. Are you with me here? Okay. So let's go with differentiability. Question is, as you approach 1 from the left, does the derivative equal the derivative as you approach 1 from the right? Does the parabola have the same slope at the point they meet as the line does? What is the derivative from the left? 4x. And what is the derivative as of the right-hand branch? It's just 4, right? I just took the derivative of each piece. And at 1, then, what does the parabola have a slope of at that point where they're meeting? 4, and obviously the line always has a slope of 4. That means then that the slope from the left, that parabola, is sloping at 4 just as it hands off to the line. Now it'll look funny, it's going to stay linear now instead of being parabolic curving. But at that point, if I zoomed in, it is locally linear. It looks like a line there. It's a smooth transition of slope. So we would conclude that f is differentiable at x equal 1. Does that make sense? Okay, you're a quiet bunch. All right then. This is a pretty common multiple choice kind of question. Let f be the function defined by this stuff. So you've got this parabola and this square root function, and they say it's differentiable. Well, that implies then that two things have to happen. I know it says differentiable, but that's actually implying two things. If it's differentiable, what does that mean the function is? Yeah, okay. Would you please write this? I should have it in a note box, but differentiability, differentiable, implies continuous. Now, that's not necessarily the other way around. I could have continuity without having differentiability, like a sharp curve, and it would be continuous without being differentiable. But if you were to think of this in a Venn diagram kind of setting, differentiability is a subset of continuity. Looking at it that way, wouldn't you agree that if it's differentiable, then it must be continuous, but not necessarily the other way around? You follow? Okay, so we're going to look at this in two cases here. Because this is continuous, we can imply that the limit as x goes to 1 from the left of the function, not of the derivative, of the function, must equal the limit as x approaches 1 from the right of the function. In other words, the branches have to meet there. All right? Now, at 1, what is the upper branch? M minus 2. At 1, x is 1, m I don't know, so it's going to stay m. So the left-hand branch will be equal to m minus 2 when x equals 1. What about the right-hand branch when x equals 1? Okay, all right. Now that's a fact that would force them to be meeting at x equal 1. If that happened, then I'd be good to go meeting. Now I also have to worry about the differentiability. Because this is differentiable, it also has to be the case that the slopes left and right of 1 have to match. So that implies that the derivative of the left-hand branch at 1 has to equal the derivative of the right-hand branch at 1. Are you with me? What's the derivative of the left-hand branch? 2mx. I'm going to do this like we typically do in 2 steps. I'm going to say there's the derivative, and I'm about to evaluate that at 1. And that needs to equal the right-hand branch. What's the right-hand branch's derivative? 2 over, what's the derivative of x to the half? K, oops, that's a K, not a 2, sorry. K over 2 root x, evaluated at x equal 1. Now if I throw that in at x equal 1, I get 2m equals k over 2. So k is equal to 4m. Great. I have 2 equations, 2 unknowns. What should I do? A little substitution at that. If they both equal to k, then surely m minus 2 must equal 4m. So negative 2 equals 3m, so m is negative 2/3, and therefore k is 4 times that, which is negative 8/3. Now with those 2 conditions, this parabola and square root function would meet and have the right slope to smoothly transition from one to the other. Pretty hard conditions to meet. You with me a little bit? Okay. I think this one should go well. Try this one on your own, please. This is a AP multiple choice from, I don't even remember now. what do you say? A, B, C, D, or E? It is true for all cases. They are all true. The limit exists because the one-sided are the same. It's continuous because the point exists and is the same as the limits, and the derivatives match at 1. So we're good to go? It is E. Excellent. All right, critical numbers. This is actually the real lesson in the book, but you'll see why you needed to talk differentiability first. A critical number is a value of x that's in the domain of the equation. Please underline that. I can guarantee you that gets forgotten all the time. Where the derivative is 0 or does not exist. Now, why do we want to find these? Because they're interesting. If I say, hey, the derivative is 0 here, in that picture, that indicates that critical number is a min. It's also possible that I could have a place where the derivative is 0, and that critical number is a max. It's possible that I have a sharp turn. In that case, the derivative is not 0, but undefined or does not exist, and therefore it's a critical number, but that critical number is a min. There are, however, actually, let's go here. What about this? If you had a graph that looked like that, would the derivative not exist at 1? F prime at 1 does not exist, but this is or is not a critical number. Well, this is not a critical number because x equals 1 is not in the domain. Now that is to say that points that don't exist on the graph are not interesting to me. I can say, hey, I wouldn't say there's a min at a point that doesn't even exist on the graph. Would you draw one more, please? Draw an x cubed graph that looks like this. F prime equals 0 here. So this is a critical number, but not every critical number makes an extrema. Sometimes it's just kind of a fake out. Oh, you thought I was going to turn back sign, but I didn't. So it's critical numbers are places that are candidates for extrema, but not guaranteed. They're good places to start looking. That's not guaranteed to happen. All right. So, if the question, for example, said, find the critical numbers of x squared natural log of x. Let's start with the domain. What's allowed to be put into that function? There are 3 restrictions on domain. In the world of mathematics, there are 3 things you can't do. What are they? Okay, well, you don't even have one of them. Come on, people. What are 3 things to break math? Dividing by 0. Boom, that's 1. Division by 0 is a domain restriction. You cannot divide by 0. Cool. What else? Rooting a negative. Boom. That's the second. That makes imaginary numbers, and we don't deal with imaginary numbers in calculus. Okay, what else? Log of 0 or negative. That's 3. Why not? Math people just said, you know what, I don't like log of negatives. Why not log of negative 2? Why can't you? Just because somebody told you so and you just follow directions like a physical nonsense? Well, that's not clean. Why think for yourself? Why? Why not? Say it again? Yeah, this is saying e to some power equals negative 2. Well, what power can you take e to get a negative? You cannot. Okay, it cannot happen. So it's just not possible. There is no log of a negative or 0. You couldn't take e to the power and get 0 like that. All right, so in this case, we're talking the case that x must be greater than 0, right? All right, now let's find the critical numbers. We need to go about the derivative. I can't find where the derivative doesn't exist or is 0 if I don't have the derivative. So, would you find the derivative, please? Now, if you said the derivative is that, I want you to take out your finger like this and go, shame on you, because that is atrocious. Is that how you take a derivative of a product? No, that's garbage. Okay? Didn't see anybody do it. All right. Derivative of a product is first stays the same. What's the derivative of the second? Plus second stays the same. Derivative of the first. All right. Cool. Now then, I want to know where this is 0 or undefined. There are a lot of algebra components to this problem. The derivative part is actually the easy part. The algebra part is the harder part. So I get x plus 2x natural log of x equals 0 or undefined, eh? Now what? Yeah, factor out an x. 1 plus 2 log of x equals 0 or undefined. So by the zero product rule, doesn't that either mean x equals 0 or 1 plus 2 log of x equals 0 or undefined? Yeah? All right, I'll come back to the undefined. X equals 0, is that in the domain? Is that a critical number? No, so that was a good candidate, but unfortunately that's not in the domain, so that is not a critical number. If I looked at the graph of x squared natural log of x, whatever it looks like, that point's not there. I don't have a critical number at a point that's not on the graph. It doesn't even exist, so that's erroneous. All right, so how about here? Natural log of x is negative 1/2. Can you take the log of a negative? No. Can a log equal a negative? Yes, it can. And so what is x here? X is e to the negative 1/2, or if you like, 1 over root e. Is that in the domain? Is that a positive number? It is, okay. So you would say x is 1 over root e is the critical number. There was no undefined place. Anywhere it's undefined wouldn't be in the domain, so that was a non-issue here. You might ask, what about those undefined? We'll get to that in a second. All right, you with me so far? All right, try this on your own then. Find the critical numbers of this. Start with the domain. hey, what's the domain? X is between. I think you'll agree X can't be too big. Otherwise, you're subtracting a bigger number and you get a negative, right? So what's the upper cap on X? What's the lower cap on X? Okay, X is between -3 and 3. Obviously, there's some graph knowledge here. Hopefully, you considered, but we'll talk about that in a second. So, what about dy dx or y prime? This is 9 minus x squared to the 1/2. What derivative technique must we use here? Chain rule. We have a derivative within a, or a function within a function. When I take the derivative on the outside, that's the derivative on blank to the half. What's the derivative on blank to the half? 1/2. The exponent drops to negative 1/2. Is the inside just the square root of x, or is it what was in there before? Yeah, so this shouldn't be, I'm seeing a lot of people when they do the chain rule, they say, oh, so the derivative of the outside is this. And no, it's not what is just like an x, it's what was in there to begin with. So what was in there to begin with was 9 minus x squared. The inside's still in. Times the derivative of the inside is negative 2x. I don't know whether it's a 0 or undefined. That's a mess. Let's write it better. Do you agree I can divide a 2 out and write this better by negative x over the square root of 9 minus x squared, 0 or undefined? All right, now here's the cool, easy part. Y prime is 0 if the top is 0. So that implies that y prime is 0 at x equal 0. Is that a critical number? Is that in the domain? Yep, that's 1. Y prime is undefined if the denominator equals 0. That implies that 9 minus x squared is 0, which means x is plus or minus 3. Are those in the domain? Was it allowed in the original function? Yeah, they were. Those are critical numbers. Now, if you think that's done, that's critical numbers, but think graphically, what does the graph of that look like? Semicircle, right? Does it make sense that I have a flat spot derivative at 0? Yeah. Does it make sense that I have a 0 in the denominator and therefore vertical tangents at 3 and negative 3? Yeah, it makes sense. And they're all interesting because they represent minimums and max in this case. Are you with me on critical numbers? Okay, so what are the 3 reasons the derivative doesn't exist? Discontinuity, vertical tangent, not vertical asymptote. Why not vertical asymptote? Because that's in discontinuity, right? Discontinuity, vertical tangent, and sharp turn. Beautiful. Okay, and then critical numbers are numbers in the domain of the function where the derivative is 0 or does not exist. And you might indicate something interesting. All right, I don't know if we have time to do one after homework, but if we do, we'll come back to that. Do you have any questions on 35? 1. Tomorrow is kind of a non-lesson because we've already done chain rules, so I intend to go over the test tomorrow. The test is in the grade book. I am very happy with how this class is going, but I just don't have time to do it today, sorry. 35, number 1. Yep. Okay. And 16, did you say? Okay. Is 16 a replacement or is it just normal? Okay. All right. Number 1, this is really the hardest part of a really difficult calculus question called optimization. And the calculus actually is pretty easy. They're trying to get you the pre-calculus part of it now. And that involves writing an equation of one variable using substitution. So they say the surface area of a rectangular solid is 100. The length and width are the same. In the base, that does not mean the height is the same. What is the volume in terms of L only, all right? So think of it like a square base. They say in the base, those two are the same. The height, I don't know what's going on with the height. It could be different, so don't think that the height has to be the same. It doesn't. You with me so far? All right, so let's start if I'm not sure this is good problem solving practice. Okay, you're not always going to know exactly what to do. So your strategies might be, all right, let me start with the question. I want volume in terms of L. That's the question. Well, what is the volume right now? Give me a volume equation. I don't mean a number. Give me an equation for the volume. Okay, length times width times height, but we said the width is length, so L squared H. You with me? All right, so I'm supposed to write V in terms of L only, so what's my sticking point now? Where do I get stuck? This isn't in terms of L only because of the H. So you ask yourself, well, the H is the problem. What can I put in for H? That goes to another relationship, a substitution, another fact. What is another relationship besides the volume? Surface area. All right, so let's get into the surface area. Wouldn't you agree that this is typically how we find surface area? And I'm thankful that I teach at this school, so that's pretty well ingrained in your head. What's the area of the base? L squared. And the surface area they give me is 100. What's the perimeter of the base? 4L. All right, and if I put the 100 in, all right, great. How does that help me? I can solve this for H, 100 minus 2L squared over 4L, so that I can use it in place of that H over there. And at that point, then you're done. They don't ask you to do any further. Later on, you'll do more. But the reason you're doing this is because it's a lot easier to do calculus on two variables, V and L, than three variables, V, L, and H. It makes it a multivariable problem. That's difficult. So the purpose of this is so later on optimization goes well. You have to practice this first. Okay? Does that make sense? Questions? Okay. 16. Is that still a question?
Yes.
Okay, 16. So let's go here. Y equals x cubed plus x. Don't you agree that x cubed looks like this by itself without the x there? And it wants to have a flat spot, but it grows and grows. X doesn't even want to have a flat spot. Keep that in mind then when I put them together, Frankenstein's monster kind of thing. When I put those together then, they're definitely going to want to do this and this. But you're going to find the combination function here is not going to even want to take a flat spot. And that's probably why you were getting confused, because you weren't actually finding a place where the derivative is 0. Did you understand? Did you get the big ideas of calculus in part B, okay? Okay, so C then was, I imagine the thing was getting stuck on. Y prime is 3x squared plus 1. Now that's saying that the rate of change for the x cubed is almost always positive with a 0 spot at 0. But then you add on to that the derivative on x is always positive, always 1. The combination therefore is never 0. If you try to solve that, it's imaginary solutions. There's no zeros to this. That implies that y prime is monotonic, one sign. Question is it always positive or always negative? It's always positive, and therefore y is always increasing. Not everything has to have a plus spot. Sometimes the function always increases, and that's not totally uncommon. You with me? So the derivative, hopefully that. Any other questions on 35? Okay, cool. Have a lovely day. I hope your week starts off beautiful. Something wonderful happens to you today. Ready to do your civic duty, Jim? Help out your fellow person, students? You're a champ. Love it.